When Richard Feynman spoke about time, he deliberately avoided poetic images of a river flowing from past to future. To him, such metaphors were comforting but misleading. He wanted people to understand that time is not a thing that moves. Nothing actually flows past us. What exists are physical systems changing, and time is simply the bookkeeping method we use to compare those changes. This idea sounds simple at first, but when followed carefully, it completely reshapes how we think about reality. Consider how we normally talk about time. We say it passes, it runs out, it moves quickly or slowly. These expressions make time feel like a substance, almost like wind or water. But Feynman argued that this language tricks the mind. If time were truly something flowing, we should be able to point to it, detect it directly, or watch it move independently of everything else. Yet we never observe time by itself. We only observe motion, decay, vibration, growth, and transformation. Time never appears in isolation. It always shows up tied to change. At the most basic level, every measurement of time depends on choosing a repeating physical process. A swinging pendulum, the oscillation of a quartz crystal, the vibration of cesium atoms, the rotation of Earth around its axis, or its orbit around the Sun. None of these are time itself. They are physical motions. We declare one cycle to represent a second, another to represent a day, another a year. Time emerges from comparison. When we say something lasted 5 minutes, what we really mean is that 5 sets of agreed-upon physical changes occurred while something else was happening. Feynman loved pointing out that if the universe were completely frozen, with nothing changing at all, the concept of time would collapse. There would be no way to say that one moment followed another. Without change, there is no earlier or later. This reveals something profound. Time is not the stage on which events happen. It is the way we label events relative to one another. Events come first. Time comes second. This perspective becomes even clearer when looking at the equations of physics. In those equations, time appears as a parameter, not as a substance. It is a variable we use to describe how quantities depend on one another. When a physicist writes an equation showing how position depends on time, it does not mean time is pushing the object forward. It simply means we are describing how the object's position changes as we compare it with a chosen clock. The math does not require time to have a physical flow. Feynman emphasized that our intuition about time flowing comes from human experience, not from physics itself. Our bodies change in one direction, we age. We remember what has already happened, not what will happen. These facts make time feel directional and alive. But that feeling arises from biological and psychological processes, not from an independent property of the universe. Memory itself is a physical process involving irreversible changes in the brain. Because memory accumulates records of changes, we interpret the direction of change as the direction of time. When you look closely, even the idea of now begins to blur. The present moment feels sharply defined, but physics does not recognize a universal present. Signals take time to travel. Light from the sun takes about 8 minutes to reach Earth. When you see the sun, you are seeing it as it was 8 minutes ago. On cosmic scales, this delay becomes enormous. Different observers, moving at different speeds, can disagree about whether 2 events happened at the same time. This shows that now is not a fundamental feature of reality, but a local and personal one. Feynman's way of explaining this avoided heavy philosophy. He returned again and again to concrete examples. Imagine 2 clocks built differently, one based on a pendulum and one based on atomic vibrations. If both are functioning properly, they agree. Why? Not because time itself enforces agreement, but because the laws of physics ensure that stable processes remain proportional to one another. If the laws were different, clocks would disagree, and our idea of time would change with them. This reveals that timekeeping works only because nature is consistent, not because time is an independent ruler laid across the universe. The idea that time is a measure of change also clarifies why physics struggles with time at its deepest levels. In quantum mechanics, particles do not always have well-defined properties until measured. Change itself becomes probabilistic. In general relativity, time is woven together with space and affected by gravity and motion. These theories suggest that time does not exist as a universal background. Instead, each system carries its own time, defined by the changes occurring within it. Feynman was careful not to claim that time is an illusion. Change is real, events happen, processes occur. What he challenged was the assumption that time exists independently of those processes. Time is real in the same way temperature is real. Temperature is not a substance. It is a measure of the average motion of particles. You cannot separate temperature from motion. In the same way, you cannot separate time from change. Time summarizes how much change has occurred relative to a chosen standard. This view also dissolves many everyday puzzles. People often ask where time goes or why it seems to speed up as we age. From Feynman's perspective, nothing is speeding up. What changes is our internal reference system. As children, everything is new, creating many distinct changes and memories. As adults, routines compress experience. The clock has not changed, our perception of change has. The feeling of time accelerating is psychological, not physical. Even statements like, "Before the universe existed, there was no time," become clearer. If there were no physical processes, no particles, no motion, then there would be nothing to compare, nothing to count, nothing to label. Asking what happened before change existed is like asking what temperature existed before matter existed. The question assumes the very thing it is trying to explain. Feynman's explanation does not strip time of mystery, it relocates the mystery. Instead of asking why time flows, we ask why change occurs in the way it does. Instead of wondering where time comes from, we wonder why the universe has laws that allow stable, repeatable processes that can serve as clocks. These questions lead directly into the deepest issues of cosmology and fundamental physics. What makes this view so powerful is its humility. It does not pretend that human intuition is the final judge of reality. It recognizes that our language evolved to handle everyday experiences, not atomic clocks or relativistic spacetime. By refusing to reify time as a thing, Feynman freed physics from unnecessary metaphors and forced attention back to what can actually be observed and measured. In the end, seeing time as a measure of change does not make life feel timeless or meaningless. On the contrary, it highlights how precious change is. Moments matter because they are unique configurations of the universe that will never repeat exactly. Time does not carry them away. Change transforms them, and in that transformation lies the true story of what we call time. When Richard Feynman discussed the strange relationship between time and the laws of physics, one of the most unsettling ideas he presented was that the fundamental rules of nature do not seem to care which direction time goes. This idea directly challenges everyday human experience. In daily life, time feels irreversible. We see eggs break but never unbreak, smoke spread but never gather itself back into a cigarette, people age but never grow younger. From this constant experience, it feels obvious that the universe itself prefers a forward direction in time. Yet, when physicists examine the deepest laws governing matter and energy, that preference almost completely disappears. Feynman liked to emphasize that physics is written in equations, and those equations are surprisingly indifferent to time's direction. If you take many of the core equations that describe motion, forces, and interactions, and you replace time with negative time, the equations still work. In simple terms, this means that the math describing how particles move forward in time also perfectly describes how they would move if time ran backward. There is nothing in those equations that labels one direction as the true future and the other as the past. To make this idea clearer, imagine filming a simple physical process, such as two billiard balls colliding on a smooth table. When played forward, one ball hits the other, energy and momentum are exchanged, and both balls move away. If you play the film backward, the balls roll toward each other, collide, and one suddenly speeds up while the other slows down. To our eyes, both versions look physically plausible. There is no obvious violation of the laws of motion in the reversed film. This symmetry is not an illusion of the camera. It reflects the underlying structure of the laws themselves. Feynman pointed out that this time symmetry is deeply embedded in classical mechanics, electromagnetism, and even quantum mechanics at a fundamental level. The equations governing electrons, atoms, and light waves do not include instructions saying this can only happen forward in time. Instead, they describe relationships between quantities that remain valid in either temporal direction. This suggests that the arrow of time we experience is not a basic feature of the laws of physics. This realization raises a troubling question. If the laws themselves are time-symmetric, why does the world look so time-asymmetric? Why do we remember the past and not the future? Why does cause precede effect in everyday experience? Feynman did not shy away from this tension. Instead, he used it to show the difference between fundamental laws and large-scale behavior. At the microscopic level, where individual particles interact, time symmetry dominates. At the macroscopic level, where trillions upon trillions of particles act together, patterns emerge that break this symmetry. The key concept linking these two levels is probability. While it is not forbidden by the laws of physics for broken pieces of a cup to spontaneously reassemble into a perfect cup, the probability of such an event is so astronomically small that it never happens in practice. The laws allow it, but the statistics forbid us from ever seeing it. Feynman stressed that this difference between allowed and likely is crucial. Physics does not say that time-reversed processes are impossible. It says they are overwhelmingly unlikely when large numbers of particles are involved. This is why everyday life feels irreversible even though the microscopic rules are reversible. The arrow of time emerges from statistics, not from fundamental law. He also used this idea to explain why memory works the way it does. Remembering something is a physical process. It requires changes in the brain, such as chemical rearrangements and energy dissipation. These processes increase disorder overall. Because disorder tends to increase rather than decrease, memory naturally points toward what we call the past. We do not remember the future because forming a memory of a future event would require a decrease in disorder that is statistically implausible. Another important point Feynman made is that even the concept of causality becomes subtle when examined closely. We usually think that causes always come before effects, but in the equations of physics, cause and effect are not always clearly labeled. The equations simply relate events. Our interpretation of one event causing another often depends on boundary conditions, such as how systems start out. In many cases, the same equation can describe a process evolving forward or backward in time with equal validity. This does not mean that physics denies causality in everyday life. Rather, it means that causality is an emergent concept, not a fundamental one. It arises because of the way the universe began and the way large systems behave statistically. Feynman often hinted that if the universe had started in a different state, with disorder already maximized, our experience of time might be radically different or even meaningless. Quantum mechanics adds another layer of strangeness to this picture. At the quantum level, particles can behave in ways that defy classical intuition. Processes can occur that seem to blur the distinction between before and after. Some interpretations of quantum theory even allow particles to be described mathematically as if they move backward in time. While these ideas are controversial and difficult to test, they reinforce Feynman's point that time's direction is not as fundamental as it feels. Feynman himself introduced mathematical techniques in quantum physics that treat particles moving backward in time as a useful description. He did not claim that particles literally travel into the past in a science fiction sense, but he showed that the mathematics works perfectly well when interpreted that way. This again suggests that the universe at its deepest level is far less concerned with temporal direction than human intuition suggests. What makes this insight so powerful is that it forces a separation between physics and perception. Our sense of time flowing forward is real as an experience, but it is not written into the bedrock of physical law. It arises from the specific conditions of our universe, the vast number of particles involved in everyday objects, and the way information is stored and erased. Feynman often warned against projecting human intuition onto nature. We evolved in a world where time asymmetry is overwhelming, so our brains treat it as fundamental. Physics, however, teaches us to distrust intuition when it conflicts with careful measurement and mathematical consistency. When the equations consistently show time symmetry, we must take that result seriously, no matter how uncomfortable it feels. This view also changes how we think about the past and future. If the laws themselves do not distinguish between them, then the deep difference we feel is not built into reality at the most basic level. The past feels fixed, and the future open not because physics demands it, but because of how information and disorder behave in large systems. The universe does not carry labels saying this is the past and this is the future. Those labels are imposed by beings like us who live inside a particular statistical flow. In this way, Feynman's explanation does not remove the mystery of time, it sharpens it. The true puzzle is not why time moves forward, but why the universe began in such a load, disorder state that a strong arrow of time could emerge at all. That question leads beyond everyday physics into cosmology and the origin of the universe itself. By showing that the laws of physics work almost the same forward and backward in time, Feynman invited us to rethink one of the most basic assumptions of human life. Time's direction, so central to our identity and experience, may not be a fundamental feature of reality, but a large-scale pattern arising from deeper, time-neutral rules. Understanding this does not make the world less real. It makes it far more surprising. When Richard Feynman explored why time seems to have a clear direction in human experience, he often returned to a single, powerful idea: disorder. While clocks, calendars, and memories convince us that time flows from past to future, Feynman argued that this sensation does not come from time itself. It comes from the way order, turns into disorder in physical systems. This insight connects our daily experience of time to one of the most fundamental principles in physics, and explains why the universe feels irreversible even though its basic laws are not. To understand this, Feynman encouraged people to think about what actually changes as time passes. Objects break, wear down, rust, and decay. Heat spreads from hot things to cold ones. Smoke diffuses into the air. These processes all share a common feature. They move from a more ordered state to a less ordered one. Order means fewer possible arrangements, while disorder means many possible arrangements. A neat stack of cards can be arranged in only one way, but a shuffled deck has countless possibilities. Nature overwhelmingly favors the latter. This tendency toward disorder is captured by the concept of entropy. Entropy is not chaos in a vague sense, but a precise measure of how many microscopic arrangements correspond to a macroscopic state. A state with high entropy can be realized in many ways. A state with low entropy can be realized in very few. When a system evolves naturally, it moves toward states that are more probable, and more probable states are those with higher entropy. This statistical tendency gives the universe a preferred direction, even though the underlying laws themselves are symmetric in time. Feynman was careful to emphasize that entropy does not force systems to become disordered in a strict, mechanical way. Instead, it reflects overwhelming probability. It is not impossible for air molecules in a room to spontaneously gather into one corner, leaving the rest of the room empty. The laws of physics allow it. But the number of microscopic arrangements corresponding to that situation is so tiny compared to the number corresponding to evenly spread air that it will almost certainly never happen. Time's arrow emerges from this imbalance of possibilities. This statistical view of time has profound consequences for how we understand memory. Remembering is not just a mental act, it is a physical process. When the brain forms a memory, it changes its internal structure. Neurons fire, chemicals move, energy is dissipated, and heat is released. All of these processes increase entropy overall. Because memory creation depends on entropy increase, memory naturally records states of lower entropy and compares them to states of higher entropy. This is why memory always points toward what we call the past. From this perspective, the past is not defined by time flowing backward from it, but by lower entropy. The future is not defined by time flowing forward into it, but by higher entropy. We remember yesterday because yesterday had fewer possible arrangements than today. Tomorrow will have even more. Our psychological experience of time's direction is rooted in this physical gradient of disorder. Feynman also used this idea to explain why cause and effect feel so natural. We say that causes precede effects, but this ordering is deeply tied to entropy. Causes are typically associated with more ordered configurations, while effects are associated with more disordered ones. A match strikes, creating a small, ordered spark that leads to a widespread, disordered fire. The reversed sequence, where a fire spontaneously gathers itself into a match, is not forbidden by the laws of motion, but it is fantastically improbable. Thus, causality feels directional because entropy almost always increases. This connection between entropy and time extends to all areas of everyday life. Aging, for example, is not driven by a mysterious time force. It is driven by physical and chemical processes that increase disorder in biological systems. Cells accumulate damage, structures degrade, and energy gradients flatten. The direction of aging follows the same entropy gradient that governs all macroscopic processes. We age forward in time because disorder increases, not because time pushes us forward. Feynman also emphasized that entropy is not about moral decline or inevitable ruin. It is about probability and scale. At small scales, entropy fluctuations can temporarily reverse. In microscopic systems, particles can briefly move into more ordered states. But as systems grow larger, such reversals become unimaginably unlikely. This is why life can exist at all. Living organisms maintain local order by exporting entropy to their surroundings. They do not violate the second law of thermodynamics. They exploit it. The origin of time's arrow, then, does not lie in the present but in the past, specifically in the initial conditions of the universe. Feynman often hinted that the universe must have started in an extraordinarily low entropy state. This low disorder at the beginning made it possible for entropy to increase over billions of years, creating a strong and consistent arrow of time. If the universe had begun in a high entropy state, there would be no clear direction, no memory, no complex structures, and likely no observers to ask questions about time at all. This realization shifts the deepest mystery. The puzzle is no longer why time flows forward, but why the universe started in such a special, ordered condition. Physics can describe how entropy increases, but it struggles to explain why the initial entropy was so low. This question connects thermodynamics to cosmology and remains one of the most profound open problems in science. Feynman's genius lay in making this abstract idea feel concrete. He did not treat entropy as an invisible law acting behind the scenes, but as a counting problem. Nature simply moves toward what can happen in the most ways. When you frame it this way, the arrow of time stops looking like a mysterious force and starts looking like a statistical inevitability. This view also reshapes how we think about the present moment, the now. We experience is a thin boundary between lower entropy states we can remember and higher entropy states we cannot yet predict in detail. The present is not a fundamental slice of the universe. It is a psychological and physical interface shaped by entropy. By linking time's direction to disorder, Feynman offered an explanation that is both deeply physical and deeply human. Our sense of time, our memories, our expectations, and even our identity are tied to the same statistical tendency that governs gases, stars, and galaxies. Time feels real and directional because entropy is real and directional in practice, even if the underlying laws are not. In the end, Feynman showed that the arrow of time is not written into the equations of motion, but into the overwhelming likelihood of how matter behaves in large numbers. Disorder does not merely accompany time, it defines the way we experience it. Understanding this does not make time vanish. It reveals that time, as we live it, is a story written by probability, memory, and the quiet, relentless increase of disorder throughout the universe. When Richard Feynman spoke about time, he often challenged the comforting idea that time behaves the same way everywhere and for everything. One of the most surprising insights from modern physics, which Feynman delighted in explaining, is that time does not tick at a universal rate. It stretches, compresses, and sometimes loses its usual meaning depending on scale, motion, and gravity. The way time behaves for a human being walking down the street is not the same as the way it behaves for an atomic particle or for a star collapsing under its own weight. At the human scale, time feels steady and uniform. Seconds follow seconds with reassuring regularity. This creates the illusion that time is a constant background against which events occur. Feynman pointed out that this illusion comes from the stability of the physical processes we use as clocks. Our hearts beat regularly, the Earth rotates smoothly, and atomic vibrations remain remarkably consistent. Because these processes agree with one another under ordinary conditions, we conclude that time itself must be uniform. This assumption breaks down when we examine extreme conditions. Einstein's theory of relativity, which Feynman frequently explained with playful clarity, shows that time depends on motion. A clock moving very fast relative to an observer will tick more slowly than a clock at rest. This is not a mechanical flaw or an illusion. It is a real physical effect. Particles created in the upper atmosphere survive longer than expected because they are moving so fast relative to Earth. Their internal clocks run slower. Time itself behaves differently for them. Gravity also affects time. A clock closer to a massive object ticks more slowly than one farther away. This means that time on the surface of Earth runs slightly slower than time aboard a satellite. The difference is tiny, but it is measurable and must be corrected for in technologies like GPS. Without accounting for this gravitational time dilation, navigation systems would drift and fail. Feynman loved examples like this because they show that strange ideas about time are not philosophical games. They have practical consequences. At microscopic scales, time becomes even stranger. In the quantum world, particles do not follow clear, continuous paths. Events happen in jumps, probabilities replace certainties, and the notion of a smooth timeline begins to blur. Feynman's path, integral formulation of quantum mechanics, describes particles as taking every possible path between 2 points. Time in this picture is not a single clean parameter guiding motion, but part of a vast space of possibilities. The classical idea of a well-defined trajectory evolving smoothly in time dissolves. In some quantum processes, it becomes difficult to say exactly when something happened. Measurements disturb systems, and the act of observation plays a role in defining outcomes. This challenges the everyday idea that time is simply there, ticking away independently of what we do. At small scales, time seems entangled with measurement and interaction. On the largest scales, time behaves differently again. In cosmology, time is tied to the expansion of the universe. The age of the universe is defined by cosmic processes, not by an external clock. Near extreme objects like black holes, time slows dramatically relative to distant observers. As an object approaches a black hole's event horizon, its time appears to nearly stop from the outside perspective. For the object itself, however, time continues normally. This duality shows that time is not a single, universal experience, but a relationship between observers and events. Feynman often stressed that these effects are not contradictions. They are clues. They tell us that time is not a rigid framework, but a flexible dimension shaped by physical conditions. Just as distance depends on how space is curved, time depends on how spacetime is curved and how observers move through it. This scale, dependent behavior of time also explains why our everyday intuition fails. We evolved in a narrow range of speeds, sizes, and gravitational fields. In that range, time behaves almost uniformly, so our brains treat it as absolute. Physics extends our understanding beyond this narrow window and reveals a much richer structure. At very small scales near the Planck length, many physicists suspect that time itself may lose meaning altogether. The smooth flow of time assumed in both quantum mechanics and relativity may break down. Feynman acknowledged that physics does not yet have a complete theory for this regime. What is clear, however, is that time, as we understand it, emerges from deeper rules rather than existing as a fundamental backdrop. This idea reinforces Feynman's broader philosophy. He believed that concepts in physics should earn their place by being useful and testable. Time works extremely well as a concept at human scales, and reasonably well at atomic and cosmic scales with adjustments. But it may not be fundamental in the deepest sense. It may be an emergent property that arises when systems are large, stable, and predictable enough to support clocks. By examining time across different scales, Feynman helped dissolve the illusion of a single, universal clock governing reality. Instead, the universe contains many clocks, each defined by the processes within it. These clocks agree under ordinary conditions and disagree under extreme ones. There is no master clock ticking in the background. This perspective changes how we think about reality itself. Events are not simply placed on a universal timeline. They are related through networks of cause, motion, and interaction. Time becomes a relationship rather than a container. In the end, the strange behavior of time at microscopic and cosmic scales is not a flaw in physics. It is a revelation. It shows that time is woven into the fabric of the universe in a subtle and dynamic way. What feels simple and steady in daily life turns out to be flexible, relative, and deeply connected to motion, gravity, and scale. Feynman's great gift was not just explaining these ideas, but making us comfortable with the fact that nature is under no obligation to match our intuitions. When Richard Feynman talked about time, he often drew a clear line between what physics measures and what human beings feel. One of his most subtle and important insights was that the time we experience in our minds is not the same as the time described by physical laws. Physics deals with clocks, equations, and measurable change. Human experience deals with memory, anticipation, emotion, and meaning. These two kinds of time overlap, but they are not identical, and confusing them leads to many misunderstandings about reality. From a physical point of view, time is defined by regular processes. An atomic clock measures time through vibrations that repeat with astonishing precision. Physics cares about such clocks because they are reliable and consistent. They allow us to compare events objectively. Two scientists in different places can agree on how much time passed because they are using systems governed by the same physical laws. This kind of time is impersonal. It does not speed up when we are bored or slow down when we are afraid. It simply tracks change according to agreed standards. Human time behaves very differently. A single hour can feel endless during pain or boredom and vanish during joy or deep focus. Years in childhood feel long, while decades in adulthood seem to shrink. These changes are not reflected on clocks. They exist entirely in the mind. Feynman emphasized that physics has nothing to say about this subjective stretching and compression. It is not a flaw in physics. It is a reminder that physics is not a complete description of human experience. The difference arises because human time is built from memory. We experience time by remembering past events and anticipating future ones. The present moment feels like a moving spotlight because our brains constantly update their internal records. Without memory, there would be no sense of duration at all. A person with severe memory loss does not experience time as a flowing sequence. Moments exist, but they do not connect into a meaningful timeline. This shows that psychological time depends on how the brain organizes information, not on how clocks tick. Emotion plays a powerful role in shaping this experience. Events charged with strong emotion create dense memories. When we look back on such periods, they feel longer and richer. Routine periods with little novelty create fewer memory markers, and feel compressed in retrospect. This explains why childhood, filled with new experiences, feels long, while adulthood, filled with repetition, feels short. Time has not changed, memory has. Feynman found this distinction important because people often attribute these experiences to time itself. They say time speeds up or slows down, when in fact it is their perception that changes. By separating physical time from human time, he showed that many everyday complaints about time are really about attention, novelty, and memory. This separation also helps clarify deeper philosophical questions. People ask whether the past still exists or whether the future already exists. Physics, particularly relativity, suggests that all events are part of a space-time structure where past, present, and future are not absolute categories. But our minds insist on a moving present. This insistence does not come from physics. It comes from consciousness. Feynman was careful not to deny the reality of experience, but he insisted that we should not confuse experience with physical description. The human sense of time also gives rise to meaning. We care about beginnings and endings. We value moments because they do not last. Physics does not assign value to moments. An equation describing motion does not care whether an event is joyful or tragic. Meaning arises from human concerns, not from physical time. Recognizing this prevents us from expecting physics to answer questions it is not designed to answer. Feynman's approach avoids both cold reductionism and mystical exaggeration. He did not say that subjective time is an illusion that can be ignored. He said it belongs to a different level of description. Just as biology cannot be fully reduced to chemistry without losing something important, human time cannot be fully reduced to physics without losing its richness. This perspective also reshapes how we think about free will and choice. People often worry that if physics treats time symmetrically, the future must already be fixed. Feynman resisted such conclusions. Physics describes patterns in nature, not the experience of making choices. The fact that equations can be written without a preferred direction does not mean that human decision-making is meaningless. Choice exists at the level of human experience, where uncertainty, limited knowledge, and memory matter. The difference between physical time and experienced time also explains why stories matter so much to us. Stories impose a human structure on time. They create beginnings, climaxes, and endings. Physics does not do this. It describes continuous processes. Storytelling is a way the human mind makes sense of time by organizing events into meaningful sequences. Feynman appreciated this without confusing it with science. In everyday life, we live almost entirely in psychological time. We plan, regret, hope, and remember. Physics time operates silently in the background, ensuring that processes remain consistent and predictable. Problems arise only when we mix these two levels without realizing it. Expecting clocks to explain feelings or expecting feelings to reveal fundamental laws. Feynman's clarity on this point offers a kind of peace. It allows us to respect both perspectives without forcing them into conflict. We can accept that physics describes a universe where time is relative, flexible, and sometimes symmetrical, while also accepting that human life unfolds in a felt sequence that gives rise to meaning and responsibility. In the end, Feynman did not try to reduce human time to equations or elevate equations into sources of meaning. He showed that understanding time requires knowing which questions belong to physics and which belong to human experience. Physical time tells us how the universe changes. Human time tells us why those changes matter to us. Confusing the two creates mystery where none is needed and hides real mystery where it truly exists. By separating the time of clocks from the time of consciousness, Feynman offered one of his most humane insights. Physics can tell us how long a moment lasts. It cannot tell us what that moment means. And that distinction, once understood, makes both science and human experience clearer, richer, and more honest.